Well, hello everyone. Thanks for attending. So I'm Etienne Carrière, software engineer at ST Microelectronics, and involved in the Opti project since quite a while. And here in this session, I will present and make an overview of the device driver support in Opti, in the hope that it will convince people that it's quite easy to add new drivers in Opti, and especially those that are interested in this trusted execution environment. So, it will be quite quick, actually. Well, I tend to speak a lot, so I'll try to not be too fluent. Mainly, we'll talk about few device drivers in Opti, and since Opti is about mainly cryptographic, we'll talk mainly about cryptographic drivers and how they're initiated. And we had some issues with the way they were initiated and dependencies, things like that. So there was another initialization process proposed using device trees, and just end up on other drivers and frameworks that are supported in the Opti. So this is about all generic Opti things, of course, in the main line, I mean. So, Opti is about cryptography. Opti is when you do something in Opti, likely you have some secret and you want someone that is really isolated to be able to access these very secrets that no one else can access. So Opti is quite related to cryptographic things. So likely cryptographic things could mean using some hardware support for cryptographic operations. Actually, Opti implements the whole cryptographic operations, as a software implementation based on the Mbed TLS or libtomcrypt, which is something configurable in Opti. Nevertheless, sometimes it's nice to have some hardware assistance for this crypto thing, starting from random number generation, because, it's better when you have some hardware assistance than the pure software random number generation, which is, of course, far less secure than that. So this is the first drivers actually that were implemented in Opti to have support for hardware assistance of crypto operations, starting so from this random number generation. And also at some stage, there were platforms that were interested in using either their hardware accelerators for some cryptographic operations, or even some more interesting things which are hardware like DPA, like more resistant to attack implementation of crypto operations, because some of the software, the Cortex-A and the software running in Cortex-A is not fully designed to be DPA resistant. Based on that, so it can have more drivers in Opti, and using drivers in Opti, hardware drivers and hardware assistance. At some stage, you may need to access some system resources to be able to use those drivers, like clock regulators, and it can then also with power management considerations. So we need to add some frameworks for power management. A last bullet I mentioned is about persistent storage. Well, when you use Opti, it's likely you have some storage. Well, you have some secrets, you want them to be persistent. The thing is, Opti, the mainline Opti currently, does not have drivers for the secure persistent storage access, because, Opti is rather using the non-secure world to access the physical media that stores this persistent, secure persistent storage, as for example an RPMB partition of an eMMC currently supported, but there are also flashes that support this, and since like storage media that are not only for the secure side but provide some generic storage medium, then usually the RPMB partition is delegated to Opti that has the key to access them, and the main part of this persistent storage is rather used by the non-secure world, likely for some file system storage. So among all those drivers I will present, you will not find some persistent storage drivers in the Opti. Well, the sole persistent storage drivers that are in Opti is rather OTP based, which is persistent storage, but it's one-time programmable persistent storage. So it's not for all some use case of trusted applications which needs to store a secret dynamically and retrieve them afterwards. So this picture is just to highlight where is Opti within the ecosystem. Opti is running on top of a secure monitor and is talking with a client that is a Linux kernel base in the mainline integration. And you may have some hypervisor, as in the secure world, non-secure world. These are optional. It depends on the architecture Opti is integrated in. So first drivers we have in Opti actually are cryptographic drivers. So as I said, Opti implements a full software implementation of the cryptographic operations, cryptographic algorithms. So the tools that are available at mainline are Mbed TLS and LibTomCrypt. By default, it's a LibTomCrypt that is integrated. It's something that is configurable. But there were some contributors that have their own hardware support for some crypto operations. And so they wanted to be able to both use the software implementation for what was not supported by the hardware, but still use the hardware implementation for the specific things they would support. So for that, it took a while. Well, it was done a few years ago, so this is not a recent thing in Opti. But it ended that there was a quite easy way to integrate a cryptographic driver in Opti, is that you have to register it at boot time. And I will show the next slide. You have to register at boot time your specific driver. You provide all the handlers for the specific operations. So here I took quite a complex one. I should have taken a symmetric cipher where you have an initialization, you have an update, a final, and it's all. This is authenticated encryption, so you have several steps and several handlers, but you still just store them in some hopes, some handler structure. You register this structure, and what will happen is that when you have some consumer, which are at the top of this slide, when they want to access a crypto operation, so they use the Opti core crypto API, and this crypto API will first ask whether there is a driver, a hardware or a registered driver for this crypto operation, and if there's none, then it will fall back to the software implementation. And the way the software implementation is made is, well, it's configurable, so you decide at configuration whether you use TomCrypt or Mbed TLS, or even if you can use some hardware acceleration of your CPU, because the ARM v8 has some hardware acceleration instructions for, so AES for sure, SHA and SM also, but I'm not, yeah, I guess if I read it, is that I found the code. So this way, you end with your, in this example, for example, you have a driver for ECC operation, for elliptic curve, operations, and maybe some AES, and all which will deal with some Edmond or RSA will fall back into this software implementation, and maybe some specific SM and SHA will use the hardware acceleration from the ARM v8. So it's an easy way. You just, if you have boot time, you have registered your crypto algorithm, then all the consumers, when they will request to use such an algorithm, they will end in your driver. So here the consumers for such operations can be internal Opti core consumers, or it could be some trusted applications, and the trusted applications through some dedicated syscalls that are implemented to Opti, and also into this crypto API and follow the same scheme. Of course, for that, you need to register your driver before anyone start to use some crypto operations, because otherwise you could fall back into this software implementation, whereas you would expect it to use this hardware, maybe DPA resistant support you provide. So you need to initialize this thing. And this comes to Opti initialization stage. Well, Opti has some init calls. I didn't put here the whole opti initialization sequence, but let's say opti initialize the basics of the CPU of the environment, and then it provides some what we call init calls, init levels. There are 7 of them. They have given some names, but actually the names does not enforce you to do something that is related. We put some names because there is some early thing, there is some service in it, some driver in it level, and a last level that allows you to release resources. But what is in the driver init level does not specifically relate to the driver. You can put anything you want from your platform at this initialization level. The important thing is here is that the cryptographic APIs and crypto layer of Opti initialize at this service init level. So if a driver or some framework or whatever of Opti needs to use the cryptographic layer API, it should initialize and start after this level, of course. And if you have a driver and you want it to be integrated into the crypto API before any consumer can use it, then it has to be initialized before. So before means either you initialize it at the early init stage or, the early init stage or the early init late stage. Actually, those init levels, initially we had 2, which was the service init and the driver init. And then we had some other drivers. There were some dependencies. We needed more levels, so we end up with 6 levels. And with these 6 levels, then we added a 7th level, just to be able maybe to release and to relax, maybe it's mainly releasing some memories that is allocated during init are no more needed afterwards. And well, 6 and 7 levels at some point are not sufficient. But well, I will come back to the next slide. Just to mention, if someone looks into this init-call.h file, you'll find that we have also 3 pre-init levels. So they are designed for specific things of Opti, as for some non-secure world, virtualization, initialization, some pager mode. Actually, in those 3 pre-init levels, only 2 are used. So they are there. If someone wants to use them, it could. Something to mention is there are also some final levels. There is a level that is called boot final. And we could expect that this boot final is the final stage initialization. Actually, the name could be a bit confusing. It's not the final boot stage. It's the final init initialization before Opti first goes into the non-secure world. So in the generic Opti implementation, all the final boot stage is done after all the init levels. But when you enable this non-secure world virtualization support of Opti, then you have all the pre-inits that are done. Then you go to this final final init level that finalize Opti before it goes into the non-secure world, where it's expected to reach the non-secure hypervisor, which will come back to when it has an instance of a first host VM in the non-secure world, and it will ask Opti to finalize the initialization. Then afterward, you will go through these init call levels. So just make sure if you use this this boot final level, that it really matches where you want it to be executed, because it could be executed before those init levels, so something worth to mention. Well, some slides, what is that? Oh, I thought I've removed it, but I've kept it. Well, this is just an illustration of what is an init call, but it looks like what there is in the Linux kernel is that you have a function, so it uses this kind of prototype. We have this tier result type, which is the native Opti return code type. So you just register with early init macro or driver init macro your function. It's called. Your function is expected to return a status, which could be T success or T error something, which could be an error. Just be careful that even if your init function returns an error status, it will only be printed in Opti debug messages, trace messages. It will not make Opti to crash. So if your initialization sequence is failing and you want your opti not to boot when it's failing, then you must explicitly call the panic function in your initialization function. I mean, why panicking in opti? Well, if you're not sure your opti is safe enough, maybe you don't want to use it. You expect your initial opti that is installed in the platform will not panic at boot time, of course. And while using some software update mechanism, especially using some dual like AB software update, then you can update to an opti that maybe will crash at init and will fall back to the previous version of optis that you would expect would run. But usually with optis, since we deal with some secure things, we tend to rather expect that some feature is available if you design your hardware and you configure your hardware to use a DPA-resistant AES algorithm, and then at boot time you find it's not there. It's really a platform decision to know whether you should fall back to a software implementation and still provide some secure feature, or whether you decide that the software implementation is not sufficient for your platform and your platform should just refuse to boot that opti. So this is basic init calls. I don't know what time is it. I hope it does not slip away too quick. As I said, we had those 6 init levels. And it comes out that, well, we had more and more drivers. Well, some platforms, the ST platform especially, had more and more drivers in opti. And so we had dependencies between our drivers. And well, with this init call, when you are at the same init call level, you cannot manage a dependency between 2 drivers. So you have to select one init call level for the drivers that must be initialized first, and another init call level for the next one. And in the end, you need pretty lot of levels. So we even ended with 6+1 levels. It was not enough, and even at sometimes some same drivers could be used in different platforms, but one platform could have a dependency from one driver to another, and another platform could have the opposite dependency. It could happen, well, specific conditions, but still we had those dependency thing to address. So a few years ago, we proposed to use device tree to describe the drivers because, well, it's fine. It's nice, a device tree to describe all your driver configuration, and it's also really fine to define the dependencies between your driver. So we proposed, and it was a lot of contributions from other people, to have DT, we'll call that DT drivers because it drivers using a device tree, to have means to probe the drivers based on the nodes that are found on the DT path to opti. Yet we have drivers that will provide support for the Crypto API framework and other drivers that will rely on the Crypto API framework. So the way it's done, it was integrated in opti, is that at init level 2, so before this service, which are the Crypto API framework initialization, we do a first loop of probing of all drivers, and maybe some those that are depending on the crypto framework would just return that they want to be deferred because they expect to use this APIs, this crypto APIs that is not yet initialized. And after the service init level, at the driver init level, we run a second loop of probing the drivers. And once the second loop is done, then we expect that all drivers that were to be probed thanks to the DT are really available. They are here and functional. And the implementation in opti, current implementation, and there's no specific configuration switch for that, is that at the end of this second driver loop, you expect to have all your DT drivers to be probed if they were there. And if some driver were probed and failed for some reason, because maybe it's still deferred because there is a dependency that is not resolved, or it failed because there were not enough memory or whatever, opti explicitly panics. So it could be a bit confusing, but with init call, if your driver does not explicitly panic, then the init call will and it returns with an error status. It will only end with a debug message in the opti trace, Whereas with the drivers that are probed using the DT, if some driver really fails, it will make Opti to panic. So that's the current implementation. If platforms are willing to have something more, well, some other way of behaving, we could add some configuration switches for that. Yeah, well, I mentioned this boot finder. Just be careful if you use something in the boot finder. The thing is, Opti does not enforce platform to use device tree. Device tree is very nice for configuring devices, drivers, establishing the dependencies of the drivers, and this dependency also can be reused in the power management sequences so that you're sure that you suspend and resume your drivers in the proper order, which will be defined at boot time. Yet, Opti does not enforce all drivers to use DDT or not, so you still can mix drivers being probed using DT and drivers or frameworks or whatever being initialized through this init sequence. One thing to mention also with this DT driver thing, there is a configuration switch in Opti, which is CFG drivers clock early probe equals yes or no. And that will make that the clock driver, well, it's legacy thing because the clock driver was the first that was integrated into this DT thing. And this will make the clock, specifically the clock driver, to be probed at the early init stage, so even before we run the loop. So it ends up that maybe you have your clock, if you enable that, your clock driver will be attempt to be probed, well, at stage 1, at stage 2, and at stage 5. But luckily, it will be probed at stage 1, it was success, and at stage 2, since it's already probed, we'll not try to probe it again, of course. The implementation just takes care of that. And all during this probe process, initialization process, again, it's quite handy to just, well, let's say even the DT probing mechanism just create lists of all the drivers that should be probed, the drivers that manage to probe, the drivers that fail to probe. We put all that in a list. And since after boot time, these lists are useless, we just release them. And this is why initially we introduced this 7th init level call to release this kind of resources. So when we use a DT driver, well, it's quite resemblant to what can be found in U-boot or Linux in the way it's like you just using some specific macro, which is define DT driver. You define your driver. You have a match table which contains the DT compatible property for matching and finding the devices that are the device nodes, DT nodes that are related to this driver. And you have a probe function that is called. And this probe function will access to the specific node, is able to extract all the DT properties that are there and initialize itself. And also with this DT, we added some other resource frameworks that allows one to request a clock because maybe one of the property is the clock's property in the node. So nothing very new. But what we had to implement there is this specific error code of Opti that is Opti error differ driver init, which will make maybe your driver probe function to be called once. It tries to get a clock, a regulator, whatever. It's not already there, so it will be probed later. It's something, it's not new idea, of course. It's things that exist in the Linux kernel since quite a while. Saying that Linux kernel has bunch and lots of drivers and devices. So we tried in the Linux kernel, there have been huge efforts to try to optimize it and not trying to probe things and differ and probe again and spend more time. In Opti, we don't have such kind of optimization because usually Opti, even all platforms in Opti do not have dozens and dozens of drivers. So it can still happen that your probe, you're deferred, you will probe again, deferred probe. It takes a bit of time, but up to date, it's not been an issue, at least for this probe back and forth mechanism. So, well, already talked about that. This driver loop. So this DT driver loop where we look at the nodes, we know all the drivers that are registered to be probed, and we just create loops of devices, and we try to call the probe function. And we establish all those lists of devices to be probed, devices that failed to be probed, those that succeeded to be probed, and once the initialization are done, we just remove this probe. And there is also a configuration switch in Opti, so that either you discover, well, you probe the initial subnodes of the root node of the DT, and then some of those nodes could be buses that will add new nodes to be probed later on, and it fills more and more those lists. Or there is a switch that can be enabled to just pass the DT in a recursive manner and try to probe every node that is in. Of course, the fact that a node has this status disabled means that it will not be probed. It's something, of course, that is implemented. As I said, with this probing using the device tree, any driver that fails to complete its probe function with an error code that is not this T-error deferred driver in it, but for another reason, will make Opti to panic. Well, and something to mention, well, the fact that you're deferred, you're deferred and probed again, it could add some latency to the Opti boot. Within so very huge latency, the biggest latencies that could lead to some dozens of milliseconds of added boot time is really parsing the DT, especially when you need to parse to look into a parent node. Because the way we use the libfdt to do that, and libfdt, when you want to get the parent of a node, you come back to the root node and you explore all the tree to find your node and know which is its parent. So it ends up looking several times the DT. And what are almost all drivers, what they first do is get their IOMEM register base address. And the IOMEM register base address means that you have to look into the parent node to know which address cells, size cells value is in the DT. So it ends up that almost every driver attempts at least one time to find their parent node. So it's something that is likely to be addressed. Started working on some solution. I've not upstreamed that. Maybe it's worth it. It was not my main issue on this boot time latency thing. But still, the way the DT is made, and if you have several drivers and big DTs, it could be maybe an issue. Just a slide to summarize what is supported with the device tree. I just recall here the DT properties to get resources. Knowing what we support is like clocks, GPIOs, pin control, they're there, I2C bus with some basic I2C APIs, NVMe cells to identify an OTP using the DT. It could be handy for some platforms, so regulators, reset controllers, and interrupts. So this helps your driver probe function to get the handle of the pin control NVMe GPIO, and then use the related framework API to use the service from this framework, being enabling a regulator, enabling a clock, or registering some handler to an interrupt controller. So to summarize, yes, somewhat. The main drivers we can see in Opti, as we said, the cryptographic drivers. So we see we have ways to register drivers in the crypto framework. And there is a function when you use the DT to make sure that you're deferred if the initialization of the crypto layer is not done yet. Also, RNG. If you have, well, the way Opti implements support for hardware and hardware RNG driver is whether, well, it's upon a configuration switch. Either you build with the software RNG, so it's CFG with software P RNG equals yes or no. And if you disable this software P RNG thing, you're expected to implement hardware get random bytes. And when you implement this function, then you end in your RNG driver, which is expected to generate those randoms, or maybe to return an error if it could not generate the expected randoms. Another somewhat hardware driver, it's not straight in the crypto API thing, but it's really related to this root of trust the service Inopti are based on. It's when you have a hardware unique key on your devices. So there is a function likely implemented in all the Opti platform, which is to be able to read this hardware unique key device unique key material. And in Opti, there is also another function which allows you to derive the hardware unique key in case maybe your hardware have support for a hardware unique key, but under some hardware API that does not even allow Opti to read the effective unique key, but only being able to operate some derivations. So there are those two functions you can implement if you support a hardware unique key or if you want to support a derivation of hardware unique key. Hardware unique key in Opti is used for isolating TA secrets from one to another. It's used for deriving the eMMC RPMB key and for many other purposes. So that's the main crypto-related drivers, and when we use them and you need to access to some clock regulators, we, as time went by, we provided frameworks for more system, what we call system resources, which are so clocks, voltage regulators, GPIO, pin control, reset, interrupt, NVMe self for OTP, and a basic I2C bus transfer API. So these APIs can be used whether you're using the DT or not. With the DT, it's easy for a driver, consumer driver, to get its clock. It will use the DT. If you're not using the DT, then you must provide to your driver the handle of the clock is that it could use using those frameworks. So these system frameworks are those that are currently in Opti, and the way it makes, we hope it's easy to extend to other frameworks if required. And what's next? Well, this slide is, this is the only slide that is not Opti generic. It's whether what's next from ST point of view. Well, there is a new framework we would like to introduce, and the pull requests have been created, at least it was last week, I think, or 2 weeks ago. It started being discussed, is providing Opti some firewall mechanism, firewall frameworks to allow some device or frameworks in Opti to either configure some peripheral access resources or just to query the configuration of it. And it's a pull request that is based, well, that propose some DT bindings, and that is based on DT bindings that were recently hacked into the Linux kernel. So there is this DT binding which is called access controllers. And now we have these access controllers bindings available in Opti. Sorry, not in Opti, it's available in Linux. So we can add in Linux firewall frameworks and services. Linux will rather query this firewall thing. And in Opti, we can use that to query the state of some firewall accesses, being memory or IOMEM resources, to query them or to query some configurations. And it, of course, depends on the platform whether it accepts or not to reconfigure this. Something that also we try to push, and well, I must rethink on that, is a secure interrupt framework. Mainly, there are two things we would like to do with secure, with the interrupt devices in Opti. Is first to allow to multiplex secure event and non-secure event on some hardware secure interrupt, and that means it rather end in allowing the Linux Opti driver to behave also as an interrupt controller, so that Opti can just tell the Linux Opti driver that there is an interrupt that arrives because it was multiplexed on the hardware interrupt that is fully managed in the secure world. And in the same scope, using this interrupt mechanism to add some wake-up capabilities related to the power management support, and so that Opti knows how to wake up when it needs to wake and have some power things. Something with, we have this new platform, STM32MP2, and what we would like is to have like a unified Opti images. You configure the way you want, but the hardware platform really description is fully driven from the DTB. It's rather from the configuration. You decide which service you want, but you really use the DTB to describe what is in the platform, what is in the board, based on this SoC, which is STM32MP2. Recently, we moved the clocks. I've added that. We moved the clocks that were operated upon a spin lock, which was not nice because some clocks were not atomic. So now that they're under a mutex in Opti, maybe there are some drivers that would still want to use some atomic clock enable, disable operations. So maybe it's something that we would need to work on. And what about unified device driver model in Opti? Well, if it's worth it, currently it's not been requested, but maybe someone would like a framework that just aggregates all the drivers that are there, maybe for some debug or trace purposes. Then I think it's done. I hope it's not too late. I tend to speak much. If anyone has questions, just feel free to contact me or some Opti guys outside. Thanks to you.